On April 4, 2018, a Piper Arrow climbed out of Daytona Beach in perfect weather with 2 experienced pilots aboard and the left wing separated from the fuselage. The airplane had 7,691 hours. It had passed every inspection it ever received. The NTSB later found that more than 90% of the fracture surface showed metal fatigue, meaning the crack had been growing for years before anyone looked. Here is what nobody told the owner. Piper already knows how to build a Spar that will not do this. They changed the manufacturing process. On new airplanes, your old one is your problem. If you own a Piper PA-28, a Piper PA-32, a Cessna 210, or a Cessna 177, stay with me. The AD wave that started with that Arrow in Daytona has now touched 21,592 aircraft. The FAA's own documents describe both new directives as interim action, meaning more is coming. What year did you buy yours, and did the pre-buy include an eddy current inspection? Drop that in the comments, and if you want the kind of analysis your A&P will not volunteer at the annual, subscribe to Sky Ranch. Every Piper PA-28 ever built has a wing spar. It runs spanwise through the lower wing, the structural backbone that transfers every load your airplane generates in flight back into the fuselage. At the outboard end of that spar, 4 bolt holes connect it to the fuselage attach fittings. Those 4 holes are where the problem lives. When Piper manufactured the Spar, they cold bent the aluminum to create the dihedral, the upward angle of the wing you see from the ramp. Cold bending means they took the extruded aluminum spar at room temperature and forced it around a die to produce that angle. The metal deformed plastically, which means permanently. And plastic deformation in aluminum does not end when the forming force is removed. It leaves tensile stress locked into the material at the bend, at room temperature. Before the first flight, before the first landing, before the first touch and go that an Embry-Riddle student would put on the logbook 20 years later. Residual tensile stress is a crack's best friend. A fastener hole in a spar under normal flight load already creates a stress concentration. The geometry of a hole in a plate under tension is inherently a high-stress zone. When you add residual tensile stress from the forming process on top of that, the bolt hole corner sees far higher stress during every flight load cycle. Higher than the engineering model predicted when Piper certified the airplane. Piper type certificated the PA-28R201 under Civil Air Regulations Part 3. That framework predates modern fatigue evaluation requirements entirely. The only fatigue language in CAR3 that touched the Spar was a vague line about avoiding stress concentrations. That was the whole standard. Cold bending the spar and then drilling the attach bolt holes through the bend radius satisfies the letter of that requirement. It creates exactly the condition the requirement was intended to prevent. No cyclic load testing was required on the specific spar bolt holes under Part 3 certification. The airplane entered service in the 1960s without a documented fatigue life for that joint. It is still in service now. Higher stress at the hole means the crack initiates sooner. It grows faster, and it grows invisibly deep inside the lower spar cap, in a location that cannot be reached by any tool an A&P carries to a standard annual inspection. The National Transportation Safety Board found this out in 2018. Piper found this out in their investigation that followed. The Federal Aviation Administration published the finding in the preamble of both September 2024 notice of proposed rulemaking documents. Residual stress from the cold bending process is a significant contributing factor in reducing the fatigue life of the spar bolt holes. Piper's response was to change the manufacturing process on all new spars. Machined dihedral bends now, no residual stress. The existing fleet received no retrofit, no recall, no proactive mailing. The owners of the 21,592 aircraft currently named in pending Federal Aviation Administration rulemaking received a number. The inspection clock is running. Here is what makes this harder. Your annual inspection cannot find this crack. The standard annual under FAR Part 43, Appendix D, requires a visual inspection of the wing structure, checking for obvious corrosion, deformation, damage. A fatigue crack propagating through the lower spar cap bolt hole interior does not produce visible external deformation until it is catastrophically advanced. The NTSB confirmed this in their report on the 2018 accident. The airplane had been through multiple annuals conducted by qualified A and Ps who signed it off as airworthy. They were not incompetent. The inspection they performed was not designed to detect subsurface fatigue cracks in aluminum fastener holes. The tool that can find those cracks is a high-frequency eddy current instrument. It uses a probe that generates an alternating electromagnetic field. That field induces circulating currents in the aluminum around the bolt hole. A crack disturbs the flow of those currents, and the instrument reads the disturbance. The physics work because a crack interrupts the path the eddy currents want to travel. The instrument reads the impedance change. The technician interprets the signal. It works on aluminum that is otherwise visually perfect. No A and P doing a standard annual is required to own this equipment. Most do not. The 2020 Airworthiness Directive mandated the first round of eddy current inspections on roughly 5,440 high-utilization pipers. Before that, no regulatory mechanism required this test on your airplane regardless of its hours. That is the gap the 2018 accident fell through. It had been falling through that gap since 1987. That year brought the first documented Piper-Spar fatigue separation, a PA-28-181 pipeline patrol aircraft in Marlin, Texas, 7,490 hours, same bolt holes, same mechanism, same result. The Emergency Airworthiness Directive that followed in 1987 set the inspection threshold absurdly high. It would not have applied to the Daytona Beach Arrow until that airplane had flown nearly another 23,000 hours past where it failed. That is not a rounding error. That framework treated a flight training airplane like a personal pleasure aircraft. In 1987, the FAA had not yet built the data infrastructure to tell the two apart. And the manufacturer had not yet documented the cold bend residual stress contribution. 31 years passed between the 1987 Marlin accident and the 2018 Daytona Beach accident. Both carried everyone aboard into the ground. Both involved the same bolt holes. Both propagated in metal that showed no external sign of distress. The Cessna story is different in mechanism. The outcome is the same. The Cessna 210 and 177 series carry their wings on a structure called the carry-through spar. It is a single forged aluminum beam that spans the top of the cabin from the left wing root to the right. Single load path, no redundancy. If it fails, both wings separate. Cessna manufactured the carry-through spar from 2014 T6 aluminum forging. That alloy is strong, and it is also vulnerable to one specific failure mode: intergranular corrosion. The attack works along the grain boundaries of the metal rather than across the surface. Early model 210S, from the 210G through the 210M built through 1979, left the factory without corrosion protection or primer on the spar. Textron's own investigation found the design made the problem worse. The upper surface of the spar sits exposed to the cabin interior, which gives moisture a direct path in. And the factory installed foam padding along the lower spar cap. That foam, intended as head protection for rear seat passengers, traps moisture directly against the unprotected aluminum. The 2014 T6 aluminum in that spar is a high-strength alloy and one of the most corrosion-susceptible in the 2000 series family. Its vulnerability is intergranular corrosion, an attack that works along the grain boundaries of the metal rather than across the exposed surface. A spar that looks clean on a visual inspection can be corroding internally, the attack working inward along pathways that run perpendicular to the surface. The eye cannot see this. The dye penetrant test a shop runs on a suspected crack cannot reliably find it in this orientation. Only eddy current testing reads the subsurface condition accurately. Cessna built a single load path forged spar that was vulnerable to exactly this corrosion. They installed it in the top of a pressurized cabin. They delivered it with no primer and no corrosion protection, and they padded it with foam that would hold moisture against the bare metal for the next 40 years. The 210 sits on the ramp. It rains, the cabin dries, the foam stays wet. It stayed wet for decades. On May 26, 2019, the right wing of a Cessna T210M separated during a low-altitude aerial survey flight in Australia. The Australian Transport Safety Bureau examined the fracture surface. They found fatigue cracking that had started at a corrosion pit measuring 0.011 inches deep, roughly the thickness of 2 sheets of printer paper. A pit that small, in a single load path forged aluminum structure with no secondary load path, grew a crack that propagated until the structure could no longer carry the load. The FAA opened an airworthiness concern sheet within weeks. The inspection data that came back was not encouraging. Among the 194 initial inspection reports on early model 210S, 110 aircraft showed corrosion, 49% of the fleet inspected. Inspectors pulled 18 carry-through spars from service. Among the 211, Cessna 177. Inspection reports the FAA received, 120 showed corrosion, that is 57%. 14. Cardinals had their spars removed from service. At the time the 2023 AD was finalized, Textron had not yet produced a certified replacement spar for the 177. The FAA acknowledged this in the AD text. Textron is still working to develop a replacement spar for those aircraft, long out of production. Some of those 14 airplanes may never fly again. Here is the irony. The carry-through spar on the Cessna 210, when corrosion is caught early and blended within limits, ranks among the more repairable findings in the fleet. The inspection, absent damage, runs the FAA's estimated $3,108 per aircraft. When a crack is present, the FAA's own worst-case estimate for spar replacement is $43,600. Real-world shops in 2026 report significantly more. The parts supply for early model 210S is limited to what is still available in certified salvage yards. One shop documented hunting for months to locate a single Cessna 210J carry-through spar. They finally sourced one in eastern Colorado for $14,500, just the part, before installation. Then only 2 of hundreds of original rivet holes aligned, and the re-skinning work began. That was the price the owner paid to continue flying a 1969 airplane that passed every inspection it had ever received. In September 2024, the FAA published 2 new proposed directives targeting essentially all Piper PA-28 and PA-32 production. Not the high utilization training fleet. All of it. The first directive covers 10,665 aircraft and supersedes the 2020 Airworthiness Directive. The second covers an additional 10,927 aircraft that were not subject to any previous Piper Spar inspection requirement. Combined fleet: 21,592 aircraft. For the models subject to the first directive, the FAA introduced life limits. An unmodified Spar on the affected models carries a life limit of 12,000 calculated service hours. A Spar reinforced with the Piper modification kit extends to 25,000 hours. The modification kit costs the FAA estimated $20,150 per wing. Real-world shops quote approximately $30,400 per wing based on current labor rates. Piper, the manufacturer that cold-bent the spars on every one of these airplanes, does not fund the retrofit. They sell the kit. Picture the owner who paid full market value for an Arrow, a Cherokee, or a 6. He bought on the strength of a clean pre-buy and a current annual. Now he faces a choice. On one side, periodic eddy current inspections at an FAA estimated $620 per event. On the other, a $60,000 structural modification that extends the spar life to a threshold most private aircraft will never reach. Both EAA and Piper itself submitted formal comments asking the FAA to rescind both September 2024 directives. Piper's position: the inspection data does not support life limits. The crack distribution, they argued, is statistically consistent with random events, hard landings, operations outside limits, not with the systematic fatigue accumulation that justifies a fixed retirement life. One owner pulled the FAA's own inspection data through a Freedom of Information Act request. His published analysis showed the crack distribution fits a Poisson process, random occurrences, rather than a fatigue accumulation curve. The FAA has reviewed the comments. As of the most recent published information, the FAA has not finalized either directive. The FAA's own language calls both proposals interim action. That means the agency plans to collect new inspection data from the expanded fleet and write further rules based on what it finds. The net grows in one direction. It has grown in one direction since 1987. 37 years of the same bolt holes, the same argument about how to count hours, the same manufacturers selling the parts that address the problem they built into the structure. The mechanic's verdict is this: get the eddy current inspection done before someone asks for it. A documented, clean eddy current result on a PA28, Pakai 32, 210, or 100 subsifen protects your value. Without it, the airplane gets discounted the moment the airworthiness directive paperwork arrives. Smart buyers are already asking for proof of eddy current compliance. Sellers who cannot produce it are negotiating from a weaker position than they realize. The inspection runs roughly $600 to $1,200 at a qualified shop. One eddy current inspection on those outboard lower spar cap bolt holes tells you whether your airplane has an active problem or a known clean baseline. Neither the annual your A and P signs every year, nor any pre-buy conducted without that equipment answers that question. The 2018 Arrow answered it the hard way, at 7,691 hours with 2 pilots aboard. The 1987 Marlin airplane answered it the same way, 31 years earlier, with the same bolt holes, the same mechanism, the same result. What Piper changed on all their new spars tells you everything about what they know. What they did not offer the existing fleet tells you everything about who bears the cost. So is this the Federal Aviation Administration protecting the fleet? Or is the Federal Aviation Administration building the data that justifies the next round of parts revenue for the manufacturer who built the problem in? One or the other, drop your answer below. If this is the kind of forensic work you want more of, subscribe to Sky Ranch.